I'm sure you all agree that it was a wonderful presentation. And the three talks so far essentially fulfilled my dream of the symposium to convey the fact that we academies and academicians have to go beyond what we are doing and take the real world into our considerations. We cannot be sitting in ivory tower anymore, because in 1945, when Bush said science is a free play of free intellect, is no longer true. That time, science and society were separated. They did not expect anything from scientists. Now, every day, there is expectation from society that the science would give solutions. To add to this, there are a few problems I like to add to for you to think before we invite the younger people, is the statistics. We do not have any statistics which is reliable. We say we are 130 million people, but I think the statements are made now that only 60 to 70% people are counted. We are in fact about 200 million people or whatever. So we are about 30%. All the estimates fail because the numbers are wrong. We do not have any kind of projections of how many doctors we need, how many engineers we need, how many teachers we need. No, everything is randomly done. And you must have seen, you open engineering colleges, next day you close it. So much of resource is being wasted. That's another thing. The third thing we need to think about is instrumentation. Today, if China says we will not supply you computer chips and computers, all your R&D, all your defense, all your finance, everything shuts down. We are already slaves in the intellectual space. And academies like INSA have to take a stand and see how to steer a country that in 10 or 15 years' time, we have a place, secure place in the knowledge space. I think these are the issues we need to be dealing with in a more harder detail. But my idea was that we essentially start thinking on these issues where we inform the policies in a real-time manner. Otherwise, very soon, we will be asked more questions and we will not be able to answer that. Shivram very elegantly present. So thank you Shivram, thank you Shashi, and thank you Ashok for starting a very good debate. Now I invite Dr. Misra to talk about theoretical physics, and so he will add more fire to the debate.
Thank you, Professor Singhvi. I wish I had known what Dr. Shivram was going to talk about, because a number of things that I'm going to say runs contrary to what he had just said. But then that's the beauty of our community. I don't feel particularly uncomfortable saying what I have to say. The thing is, as I said in the abstract, I'm going to make a case for funding of theoretical sciences. The funding is little. Whether the government should fund it or who else should fund it is a question that I want to debate. The other issue that I want to quickly get out of the way is the question of when research is funded in a particular country, whether the outcome of that research benefits that country. Now this can be really taken to extremes, where you can ask research that is funded at IISc, does it actually benefit Karnataka? Does it benefit Bangalore? And so on and so forth. Consequently, while such questions are raised, what I would like to know is whether we should give in or we protest and say that no, this is not acceptable. There are ways in which we all benefit from each other. While there are geographical boundaries, we would like to, as a scientific community, cut across all that and benefit from our knowledge. So with that, although this is about the future, I would like to mention just a little bit of how things have been, where we are today, and then talk about the future. I'd like to do all that in about 20 minutes time. The point is, goes back to when we talk about theoretical sciences, sometimes I will talk about mathematics. Please understand that I'm not making a case for mathematics. I'm trying to make a case for everything that is theoretical. So mathematics often is sort of poetic when it comes to abstracting a problem, but on the other hand, it's very effective in solving problems in real science, and there lies the duality. Is it really art or science? And there are many examples in the past where it has played both the roles. I want to talk just a little bit about a very modern and recent subject. This is called knot theory, and as this one says here, somebody asked, what's your favorite subject? And the student says knot theory, and the other guy of course responds by saying me neither. Now at this point, of course, knot theory as a subject was not even understood among even university students, but here is something that I would like to describe. So knot theory as a subject was inspired when people thought that the world was full of ether, and then ether consisted of material that were like knots, knots had strands, and so on and so forth. This was before one realized the physical reality was sort of explained in terms of atoms. So when atoms came along, the scientific community at least forgot about knot theory or knots. On the other hand, mathematicians remained hooked with this idea of knots. What happened then was that somebody who is in Israel today, Aman, he did his doctoral thesis way back in the early 50s in knot theory. And here is an anecdote. While giving a lecture, he himself said, in his PhD thesis, he proved that knotted knots cannot be unknotted. In fact, one of the principals in recent times went to somebody who essentially proved that two different kinds of knots are not actually the same. So he says he worked very hard on this problem and proved that this result after working hard on his PhD problem. But then the thing is, who cares? Well, as you will see now, here is a little anecdote. He says he is now in his 70s, and he says while he was sort of relaxing one evening, his grandson calls him and asks, what is the linking number? Now, this old, he kind of was surprised that his grandson, who is doing biology, should be asking about linking numbers. So, with a little surprise, he said, well, you mean linking numbers as in knot theory? This young man responded, yes, linking numbers as in knot theory. And of course, his grandfather responded by, but why do you care? And he was told that he was taking a biology class where the professor explained knots, and he says that, well, I did not fully understand, and therefore I am asking. So, so these are the kind of knots that one these days sees in biology. Yeah, okay. So the point about abstraction, of course, is that in reality the DNA strands or what was imagined to be ether or protein or whatever, they look like this, but then as far as looking at them mathematically is concerned, you can make up isomorphisms that then take you to structures of that kind. How many different sorts of things like that there are is what makes the subject exciting. So, this is one of those examples that I wanted to make, which is not too far away in time. This is in 50s that knot theory was being studied, and by the time we come to the beginning of this century, in biology, knot theory is beginning to play a rather fundamental role. So to separate these ideas, I think would be a mistake. Here is an example which goes back further in history, and since we are talking about politicians and others in the previous talk, let me just say this is an anecdote. Gladstone, looking at some of the experiments of Faraday, says, but after all, what use is it? And here is the answer. Why, sir, there is every probability that you will soon be able to tax it. Now, of course, that soon might mean few months or few years, The point is, if we chose to argue, whether it is with politicians or other community leaders, I don't see why we cannot make an argument. I mean, these are examples to support that. Here is the similarly, when radium was discovered by Marie Curie and Marie Curie way back again, 1898, she herself says we must not forget that when radium was discovered, no one knew that it would prove useful in hospitals. The work was one of pure science. So there are many examples, and this is a quote from her. Scientific work must not be considered from the point of view of the direct usefulness of it. It must be done for itself, for the beauty of science, and then there is always the chance that a scientific discovery may become like the radium, a benefit for humanity. There are 3 or 4 examples of this kind where one talks about GPS, one talks about Google, one talks about gamma knives that are used in surgery these days without really actually cutting open a human body. All this is possible based on mathematics or ideas that go back even hundreds of years. GPS is possible because spherical geometry was discovered, who knows what, maybe a few hundred years ago. That's how the satellites and whatever they find very well. And in here, one says that the Pythagorean theorem alone, the theorem which is the Pythagorean theorem that one learns in high school, and those related to it have given us our entire system of measurements. It allows pilots to navigate in windy skies. Now you might argue that after Pythagoras discovered his Pythagorean theorem, if we were not to find aeroplanes to fly, then there would be no use for the Pythagorean theorem. There is always that. But then to sort of anticipate whether something will happen or not is a very tricky and dangerous business, I would say. So it allows pilots to navigate in windy skies and ships to set their course. All GPS measurements are possible because of this theorem. I won't quite say that, not exactly this theorem. It's a bit of spherical geometry and so on and so forth, which is not very old. The point is, it's perhaps 300 years old. Now coming to present times, these are things from way back. There has been a 2010 report. Since we are talking about future, particularly in our country, we have seen in the past there has been a lot of uneasiness, let us say, communities that work in different areas, different sort of style, different ways of thinking, and so on and so forth. So this report, for example, sort of talks about the distinction between pure and applied. Here, of course, it means pure and applied mathematics in particular, then mathematics and statistics. The point is, they have produced an increasingly negative effect by stressing divisions rather than the unifying effect, and the features that unite mathematical sciences dominate those that divide them. This is kind of the report. I am happy to say that we have come a long way over the last many years in actually sort of removing these boundaries. I remember 30 odd years ago when I started this whole business about what is pure and what is applied. It used to be a very big sort of point of argument between people, but that has become much less. And going forward, we must ensure that these boundaries don't come back to us, and the walls between statistics, mathematics, pure and applied, they are completely removed, whatever form they might exist today. Here is a current example also about what Dr. Sivram was saying about government funding and such. This is a very recent example from Duke University. Siva Patek, she had asked for some NSF funding or something, and the lawmakers, their criticism was she was working on some shrimp and some ants and whatever, with some calling her government-funded studies a waste of taxpayers' money. This was in the US. Apparently, some senators made her research was evaluated and there was this opinion expressed. But according to Patek, no, not only do her funding have important practical applications, but scientific inquiry is most fruitful when knowledge is sought for its own sake, not to justify budgets. This is happening in current times. There are people who are standing up to the government. My point is, just because the government is telling us something, they are thinking in a certain way, we don't have to align ourselves to the thinking that we perceive that the government has. We can have our own thinking. If worse comes to worse and we have to give up on government funding, so be it. But this whole business about whether we benefit from the funds that were given to us by our government is something that we must not bother to answer, is what I feel. Going into the future, there are areas, there are possibilities for our young graduates that we must create. What areas where we must have opportunities to make a difference, both in terms of our scientific position and be able to excel. In fact, I often say, Indian Statistical Institute way back was in a leadership position when it comes to the world in terms of excellence in statistics. Over the years, we have lost that. I'm not entirely sure in which other subject we are absolutely on top of the world. Now, when it comes to policy making, wondering about what we should do in future, one of the things to think about is that when a subject is young, we must get in and perhaps try to do well. Given the number of young people who are really very willing, very eager to do research, we should identify those areas. There is a mistake here. This should not be computer-assisted proofs. It should be computer verification of proofs. There have been very, very interesting things in the recent past where theorems that were proved were accepted to be correct. There have been some issues and problems with their proofs, and there is a new area that is emerging which says that many complex proofs that cannot be, or that's not easy to verify by humans. We perhaps must have algorithms and machines that don't prove the theorems, but they verify that the theorem is correct. Why is that? Well, formal verification is a rapidly growing field of computer-assisted proof verification. So that's what I mean. It's a proof verification. Formal verification offers an assurance of correctness far beyond other forms of testing. In safety critical systems, like in a hospital or elsewhere, even an occasional failure is not acceptable. The driverless trains of Paris Metro use formal systems for verifications of their algorithms. And let me say here that actually the Paris Metro sent a bunch of their engineers to come to the mathematics department at IAC and take a whole semester-long course which were taught by Siddharth Gadgil and Kamal Lodhia for a whole semester on this formal verification of algorithms and proofs. So it's actually happening. A formal verification goes in power. One could hope to use it in many other areas and to much greater extent. Yet, this is a small field with a small community working in it, so that the potential for making significant contributions is high. So the point I'm making is that the more we know about such things, the more we encourage others to work in these sort of topics, I think we will be doing well. There is another, I have another 5 minutes or, yeah, good. So another emerging area where we are getting into a very difficult situation reminds me of how statistics used to play a role where politicians and other people sort of didn't fully understand various of these statistical methods, and yet we are happy to draw conclusions very often erroneously. There has been a recent incident involving our voting machines, and I'm sure my colleague Rajiv Karandikar will talk about it tomorrow, but I want to talk about here something related but of a slightly different nature. It says, can we keep up with artificial intelligence? So a tank that drives itself, a drone that picks its own targets, a machine gun with facial recognition software. Okay, sounds like science fiction. Weapons powered by artificial intelligence are already here. Now, killer robots aren't regulated yet. Okay? AI experts calls for end to UK use of racially biased algorithms. Okay? Senators protest health algorithms biased against black people. Recruitment algorithms are infected with biases, AI experts warn. Algorithm bias in credit scoring, what's inside the black box. So the point of my showing you these snippets, these are basically, if you like, newspaper headlines, more or less. I don't want to go into. This is a growing area of research. I started by mentioning how statistics was perceived, and everybody started saying, oh, there is this data, there is that correlation, and so on. Some terms were thrown around. And after that, we have come to the stage where AI or machine learning or this or that are going to be some keywords that will be thrown at the public, and then you will say, well, because my algorithm made me do so, therefore these are the results. Now this is where again there is a great opportunity for social scientists, experts in algorithms, mathematicians, and so on and so forth, to put their heads together and understand actually what is going on. Otherwise, this is going to have disastrous effects on society. And again, my point of mentioning this here is that this is an area, if there were a policy decision that we can make to encourage some of these areas, this is what might take us to positions of leadership worldwide. I mean, gone are the days when we should be looking for, the call center, this, that, and perhaps the little jobs fixing routine software problems. These are the emerging. The past few years I've seen growing recognition that this, machine learning raises novel challenges for ensuring non-discrimination, due process, and understandability in decision making. Okay, so this is a new sort of development. In particular, policymakers, regulators, and advocates have expressed fears about the potentially discriminatory impact of machine learning, with many calling for further technical research into the dangers of inadvertently encoding this into automated decisions. This automated decisions is a very, very new sort of thing that's happening. So much so in America, for example, the criminal justice system, they are saying they can automate the criminal justice system. You feed in data, and then the algorithm tells you what is the judgment. So this has to be looked at carefully. Although I am not exactly an expert, or I don't know very much about these things, but I must mention the issues involving climate change, and no challenge poses a greater threat to our children, our planet, and future generations than climate change. There is no doubt, as we have seen earlier from many other lectures before me, that the cogestion economy, carbon emission, global warming, climate catastrophe is the consequence. The possibility of unexpected changes is very much there. The finiteness of the world did not play a role in the past. There was enough room for polluting. We have been doing it happily. But the trouble with monsoon and the threatening problems with the great rivers caused by melting of Himalayan glacier will cause misery sooner and more heavily in India than most other places. Technological research into efficient agricultural practices and food production in general is very important. I just want to say one line here. In Odisha, which happens to be my home state, there were about 15 years ago, there was a big cyclone. Many thousand people actually died. A lot of property destroyed. 3 years ago, there was a cyclone, perhaps of even a larger magnitude. But the damage caused was much, much less. Perhaps only, if I am not mistaken, there might not have been even any loss of life. This was possible partly because the trajectory of the cyclone was predicted absolutely accurately. So, as far as going forward to the future, I have already sort of embedded that into the previous slides by saying what we should be doing. But I have one or two concerns. There are only 2-3 slides here that I will finish quickly now. Basic science research deserves support because in history it was always true that research pursued for its own sake was what led to huge, generally unexpected technological consequences that made life in the world easier. Now this is not possible to, but it should also be emphasized that basic science cannot work on order. You cannot tell, well, this is what you want, and then the scientists sitting in their lab would produce that. Actually, in the previous lecture, there was a reference to such questions. There is something about science evaluation that I want to talk about. What has happened in the very recent past, we have started evaluating the research of our younger colleagues, PhD students, young postdocs, and so on, in a more or less continuous manner. And as far as I can see, many of those people are stressed way beyond what I would call healthy. And as a result, I think they are not able to produce or are not producing the kind of research that you will expect from them. In fact, one of the consequences of that is that we have a voluminous whatever in terms of research, but if you ask me, the depth has actually not been so great. Particularly in mathematics, where I can attest to the fact that the kind of research has been very impressive. I mean, the depth is lacking, whereas number of papers that we produce are very large, and this is because of the stress that we create for our younger colleagues by asking them every 3 months, what have you done? But well, that doesn't, in particularly in theoretical sciences, it's very hard to say what I have done in the last 3 months. So the competition to seek funding, fellowship, hours, etc. hasn't been very healthy. This is also another thing I want to say. Maybe all of you are aware, but the evaluation system that we have for various of these possibilities are not perceived as something that's completely transparent and fair and so on and so forth. So there is a lot of uneasiness. Many of our younger colleagues feel that they have to go through the system, but then they don't believe in the system. Some of us have to do something so that we create this impression that we are a community that actually acts with conviction and without any bias and without any other. Finally, this is the last slide. Evaluation of research should be based on the quality attested by experts in the field. This can be in the form of reports that can be shared. Actually, at this early stage, it is necessary that again, when we are doing an evaluation, the reports of these evaluations, what we think should be debated and perhaps can be even debated openly. And same with research proposals and other decision-making processes. And one last thing is that we keep talking about teachers, we keep talking about all of us who have to teach, but teaching, of course, is a rather crucial part of what we do. And I would like to propose that rather than just saying that we give these teachers hour and so on and so forth, which is a significant first step, perhaps we should find ways of creating a fellowship for teachers at various levels. Thank you very much.